Welcome students to MOOC's series of lectures on non-parametric statistical inference. This is lecture number 7. As I said in the last class that in this lecture we shall study tests for randomness. Now, random process or random number or random graph, random indexing are certain terms which are nowadays very important because of machine learning, but from a statistician's perspective most important thing is random sample. Question is, what is random? Cambridge Dictionary gives this is the definition of randomness, that is happening, done or chosen by chance rather than according to a plan. So, when we talk about drawing inference about a population or about a distribution, we often take a random sample. What does it mean? It means that sample is taken without any bias or pre-designed rule of selection or to support some purpose, etc. Therefore, when we have a data, we need to test the randomness of the data. How to do that? In order to check whether something is random, it is very important to maintain the order in which the samples are chosen. If we consider the data points only as a set, then we lose the flavor of randomness, because the order in which the data points have been chosen, that is very important, as I am going to illustrate now. Suppose you are taking 12 balls from a basket with a large number of red and blue balls. Now, we have taken 6 red balls and 6 blue balls. Suppose the order of selection is this: first 6 are blue balls and the second set of 6 are red balls. Will you consider it to be a random selection? No. What about this? If we choose it alternatively blue, red like that, then do you consider this to be a random selection? Again we understand that that is not random. Let us consider a third example. If the pattern of selection is like this, first 3 R's, then 6 B's, then again 3 R's, we understand that there is a specific way of selecting the balls from the basket. Therefore, this also is not random. However, if we consider this selection red, blue, red, then blue, then again red, then blue and red, then it appears that the selection of red and blue ball from the basket is rather random. Question is, how do we test? Because all the 4 selection orders are having 6 blues and 6 red balls. So, that is the basic question, how to test whether a particular sequence is random or not. The basic theory developed in test of randomness is based on the concept of runs. So, what is a run? Given an ordered sequence of 2 or more types of symbols, a run is defined to be succession of one type of symbol that is succeeded and preceded by another type of symbol or no symbol at all. So, let us consider the 4 selection orders that we have just seen. With respect to the first one, this is one run of blue balls, because there is no red ball in between. It is a continuous sequence of observations of 6 blue balls. Similarly, a continuous sequence of observation of 6 red balls. Therefore, how many runs are there? There are 2 runs. This is succeeded by this run and this sequence of R balls is preceded by the sequence of blue balls. Consider the second one. How many runs are there? There are 12 runs, as I have explained here. This is one run blue, it is intercepted by a red, again that is intercepted by a blue, then red. So, like that there are 12 number of runs in this sequence. With respect to the third one, we can see that this is one run of R, this is one run of blue, and this is one run of R again, that gives us 3 runs. And this one very similarly, first run, second run, third, fourth, fifth, sixth and seventh. There are 7 different runs in this sequence. What does it tell us? So, it is clear from the above example that if the number of runs is too large or too small, then it is unlikely that the points are chosen randomly. However, what is too large and what is too small, that depends upon the composition of the data. For example, we have in the previous illustrations 12 balls, of which 6 Bs and 6 Rs. That means 6 are blues and 6 are reds. Therefore, maximum possible run can be 12. Of course, the minimum will be 2. One sequence of red and one sequence of blue. However, suppose there are 10 Bs and 2 reds, then the maximum number of runs can be 5. One sequence of blue, one sequence of red, maybe one red, one sequence of blue, one red and another sequence of blue. This is the maximum number of runs that can be achieved from 10 blues and 2 Rs. Thus, the maximum number of runs is 5, although the minimum will still remain 2. Therefore, when we are talking about if the number of runs is too large, we have to be very careful about the composition of the data as well. Now, the tests based on runs are applicable to either quantitative or qualitative data. It is not necessary that the data has to be numeric. It can be symbolic, as we have already seen sequence of Rs and Bs in our previous illustrations. However, in the case of numeric data, typically the dichotomy is affected by comparing each number with a focal point which can be median or mean. What do we mean by that? Dichotomy means that when there is a sequence of numbers, how do we split it into 2 different sets like R and B? In sign test we have seen plus and minus. So, how do we do that? So, that is done by comparing with median or mean. For example, suppose we have taken 12 real numbers between 50 and 100. So, this is one sequence 95.6, 88.3, 75.8, like that 59.2. Another sequence is 59.2, 88.3 and up to 60.6. Which one of them is random and why? To test that, what we do? We first compute the mean or median. In this case, median is coming out to be 72.8, because this is sort of the average of these two. Then what we do, as we did in the case of sign test, we consider how many of these observations are bigger than the median and how many of them are smaller than the median. The same we do with respect to this sequence of observations as well, and we find the following. With respect to the first one, we get that there are 6 plus followed by 6 minus. Therefore, number of runs is 2. However, with respect to the second sample, we get minus, plus, plus, another minus, plus, then one minus, plus, minus, minus, plus, plus, minus. That means, the 6 plus and 6 minuses are very nicely intermingled among themselves, and we get that the number of runs is equal to 9. Now, if I ask you which one of them is random, we can easily see that this is definitely random and this is definitely not. So, while working on numeric data, this is one we resolve the dichotomy and thereby we can solve the randomness problem, and we can check if the data is actually random or not in the following way. However, if we have a numeric data, there is another important test which is called runs up and down test, which we will do later, but before that let us just study the common what is called run test. So, the run tests are based on the total number of runs in the sequence. Assume an ordered sequence of n elements of two types A and B, with n 1 of them being A and n 2 of them are B, such that n 1 plus n 2 is equal to capital N, it is the total number of data points. With respect to the previous example, n 1 was 6, n 2 was 6 and n was 12. In order to derive a test of randomness, we need to obtain the distribution of R. What is R? R is the total number of runs, which is R 1 plus R 2, where R 1 is the number of runs of A and R 2 is the number of runs of B. Now, what is the total number of possible arrangements of n elements? When there are n 1 of them are of type A and n 2 of them are type B, the number of possible arrangements is n 1 plus n 2 C n 1 or equivalently n 1 plus n 2 C n 2. Why? Some people often ask, because arrangement is a permutation problem, but this is a combination. So, how do we interpret a permutation problem using a combination? The answer is simple, because n 1 plus n 2 many elements can be arranged among themselves in n 1 plus n 2 factorial. However, n 1 of them are same and n 2 of them are same, therefore, we need to divide it by n 1 factorial, n 2 factorial, and this is nothing but n 1 plus n 2 C n 1, which we have written here. Okay. Now, the number of distinct ways of distributing n like objects into R distinguishable cells with no cell empty is n minus 1 C R minus 1, when n is greater than equal to R. This is a very simple combinatorics problem. So, suppose for example, I have 7 balls and I want to put them in 3 boxes such that no box is empty. In how many ways one can do that? So, let us first understand that in order to put them in 3 boxes, we need to draw some partitions there. So, let us consider I draw these 2 partitions. Therefore, in the first box there are 2 balls, in the second box there are 2 balls, in the third box there are 3 balls. So, this we can write it as say 2, 2, 3. Another example, suppose I have again 7 balls and I choose the following lines, then what do I get? We get 1, 3, 3. Therefore, each selection of 2 lines out of the 6 empty places between the 7 balls 1, 2, 3, 4, 5, 6. The number of ways of choosing 2 out of 6, that is going to give me 3 partitions, each one is non-empty. In general, therefore, when there are n objects to be put in R boxes, when n is greater than equal to R, number of ways of doing it is n minus 1 C R minus 1. Now, we had n 1 objects split into R 1 runs and n 2 objects split into R 2 runs. Therefore, number of ways of doing it is n 1 minus 1 C R 1 minus 1. Number of ways of doing this is n 2 minus 1 C R 2 minus 1. Therefore, total number of combinations is n 1 minus 1 in C R 1 minus 1 multiplied by n 2 minus 1 C R 2 minus 1. Why we are multiplying? So, let us understand that. Suppose this is one sequence of blue balls. Now, in order to make these 3 to be runs, in each of these we have to fill in some objects of the different kind. So, if these are blue balls, one, 2, 3. So, to make these runs separate, we have to insert some run of red balls. And if these partitions of 2 runs can be done in k different ways, so we can fill it in k different ways. Therefore, the number of ways of making 3 blue ball runs multiplied by the number of ways of making 2 red ball runs will give me 5 different runs. That is why we see that this comes to be n 1 minus 1 C R 1 minus 1 multiplied by n 2 minus 1 C R 2 minus 1. Also note that very interesting thing that R 1 and R 2 cannot be very arbitrary. Given R 2, R 1 can take values R 2 plus 1 or R 2 minus 1, or R 1 can be equal to R 2. Say for example, if these are the runs of R 2, 3 runs, then there can be 3 possibilities for R 1. R 1 can be 2, R 1 can be 3, or R 1 can be 4. So, if R 2 is equal to 3, R 1 can take either 2 or 3 or 4. It has no other possible choice, because if there are more elements of the first type, then actually we will combine them into one run. So, with these observations, we get the following. To obtain the probability that R takes a value small r, where r is the total number of runs, therefore, small r can be either even say 2d or odd, that is 2d plus 1. Now, if the total number of runs is 2d, that is even, then both R 1 and R 2 have to be equal to d, and the sequence may start with either A or B. Similarly, if R is equal to 2d plus 1, that is odd numbers, then R 1 can be d plus 1 and R 2 can be d, or alternatively R 1 is equal to d and R 2 is equal to d plus 1. In the first case, the sequence starts with A and also ends with A. In the second case, it starts with B and also ends with B. Therefore, probability that r is equal to small r is computed as follows. Number of ways that r 1 can take value d is n 1 minus 1 c d minus 1, just some time back we studied this. Similarly, r 2 can take value d in n 2 minus 1 c d minus 1 ways. Therefore, the number of ways that r can be 2 times d is 2 into n 1 minus 1 c d minus 1 multiplied by n 2 minus 1 c d minus 1. Why the 2 is coming? It is coming because it may start with A and end with B, or it may start with B and end with A. Therefore, probability r is equal to 2d is equal to 2 star n 1 minus 1 c d minus 1 multiplied by n 2 minus 1 c d minus 1 divided by n 1 plus n 2 c n 1, as this is the total number of possible runs. In a similar way, probability r is equal to 2d plus 1 is equal to n 1 minus 1 c d multiplied by n 2 minus 1 c d minus 1. That is, this is the case when there are d plus 1 runs of the first type and d runs of the second type, plus n 1 minus 1 c d minus 1 multiplied by n 2 minus 1 c d. That means, d runs of the first type and d plus 1 runs of the second type divided by the total number of possibilities, that is n 1 plus n 2 c n 1. Let us now consider for illustration a case with n 1 is equal to n 2 is equal to 5. Therefore, probability that r is equal to 2, that is number of runs is equal to 2, that is coming out to be from this formula 2 upon 252, which is 0.008. Now, what is 2? 2 is equal to the number of arrangements that satisfy that total number of run is 2, and we know that it can be only in 2 ways, that is A and A followed by B, 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 B and B, or it can be B followed by A. There are only 2 possibilities to have total number of run is 2. In a similar way, probability r is equal to 10, that is also coming out to be 2 upon 252 by applying the formula, and here also we can justify the same, that the number of run is 10 if we get A B up to A B or B A up to B A. So, this formula, whatever it is giving, is correct from practical justification. What about the probability of r is equal to 6? So, the same formula, by applying the value of d is equal to 3, we get is giving us 72 upon 252, which is 0.2857. Question is, how do we get 72 many arrangements to give us 6 runs? So, 5 A's can be arranged into 3 runs in 6 different ways. Similarly, 5 B's can be arranged into 3 runs in 6 different ways. Therefore, number of possible arrangements is equal to 2 times 6 into 6 is equal to 72. Thus, from here also we get the correct answer. Now, the question is, what are the 6 different ways? If we look at, we have shown it to you that 5 elements can be put into 3 runs. The possibilities are 3, 1, 1 or 2, 2, 1 and similarly 1, 3, 1 and from here we get 1, 1, 3. So, these are the only 6 ways of splitting 5 elements into 3 runs. So, that is what we have applied there for both A and B and our ultimate answer came out to be 72. In a similar way, we can handle odd number of runs as well. For example, consider r is equal to 7. Therefore, by applying the formula, we get the number of such runs is 48. So, that probability of 7 runs is 0.190. Now, the question is, how do we know that there will be 48 runs? That comes from this calculation. Just now we have seen that probability of 3 runs of 5 elements is 6. Now, getting 4 runs out of 5 elements, there are 4 possibilities. We can have them 2, then 1, 1, 1 or 1, 2, then 1, 1, 1 and similarly from the other 2 you can understand the partition into 5 runs. Therefore, 6 from here and 4 from here, therefore, total number of runs is 2 into 6 into 4 is equal to 48. The 2 is coming because we may have 4 runs of A and 3 runs of B or alternatively 4 runs of B and 3 runs of A. So, that is why the factor 2 has come, but at the end this justifies why the formula gave us that there are 48 many different possibilities of arranging the elements such that total number of run is equal to 7. Therefore, we have probability r is equal to 7 is 0.190. In a similar way, we can calculate that probability r is equal to 8 is 0.127, probability r is equal to 9 is 0.032, probability r is equal to 10 that we have already obtained is 0.008. Now, if we look at the right tail probabilities, we can see that by adding the terms probability r greater than equal to 10 is 0.008, r greater than equal to 9 is 0.040, r greater than equal to 8 is 0.167 and r greater than equal to 7 is 0.357. Why did we calculate that? Because we need these values to accept or reject the null hypothesis, and for that we need to look at a table with right tail probabilities. So, here is the table and we are considering number of A and number of B is to be 5 and 5. So, if we look at, we can see that the right tail probabilities for 10 is 0.008, for 9 0.04, for 8 it is 0.167 and for 7 it is 0.357. Therefore, we see that we have obtained the same values through our calculations using the formula for obtaining the run probabilities. The above table giving the right tail probabilities is taken from the book Non-Parametric Statistical Inference written by Gibbons and Chakraborty. Now, large sample approximations, when either n 1 or n 2 are greater than 20 or both are greater than 10, then one can approximate with normal distribution with the following parameters. The mean is coming out to be 2 into n 1 into n 2 divided by n 1 plus n 2 plus 1. Note that we are using the notation m and n for the number of elements for the two populations. Here it is given n 1 and n 2. So, m is actually the n 1 and n is actually the n 2. Therefore, variance of R is given as 2 into n 1 into n 2 multiplied by 2 n 1 n 2 minus n 1 minus n 2 divided by n 1 plus n 2 whole square multiplied by n 1 plus n 2 minus 1. This is a complicated expression. We are not going to derive it here in this class. Let us accept this formula. The test that we have described so far based on the runs is called Wald-Wolfowitz run test. So, some simple mathematical observations on the number of runs. What is the marginal distribution of R 1, where if you remember R 1 is the number of runs of the first element. We know that the minimum value for R 1 is 1 and the maximum value of R 1 is n 1, that is the number of elements. Therefore, given n 1 and n 2, the random variable R 1 can take value integral values in the set 1, 2, 3 up to n 1. To compute probability R 1 is equal to small r 1, we do the following. If R 1 of small r 1 is equal to the joint distribution of R 1 in R 1 comma R 2, that means the number of runs of the first element and number of runs of the second element are same. We have already seen that this value can be same or plus minus 1 of R 1. Therefore, we also add to it the probability of f R 1 R 2 of R 1 and R 1 minus 1 and similarly R 1 and R 1 plus 1. We know all these values, this we have already computed. This is 2 n 1 minus 1 C R 1 minus 1 multiplied by n 2 minus 1 C R 1 minus 1. Similarly, from this we get this and from here we get this. This we are getting by replacing the value of R 2 with the corresponding parameter in the relevant expression. Now, we need to simplify this. How we simplify? So, let us look at it. So, n 1 plus n 2 C n 1 multiplied by f R 1 of small r 1, that is, this is the marginal distribution or marginal probability. Therefore, it is writing as 2 into n 1 minus 1 C R 1 minus 1 multiplied by n 2 minus 1 C R 1 minus 1 plus n 1 minus 1 C R 1 minus 1 multiplied by n 2 minus 1 C R 1 minus 2 plus n 1 minus 1 C R 1 minus 1 multiplied by n 2 minus 1 C R 1. Now, let us take n 1 minus 1 C R 1 minus 1 common and we write 2 times this as summation of this. Therefore, we are getting n 2 minus 1 C R 1 minus 1 and another one we write it here n 2 minus 1 C r 1 minus 1, n 2 minus 1 C r 1 minus 2 plus n 2 minus 1 C r 1. Now, summation of n 2 minus 1 C r 1 minus 1 and n 2 minus 1 C r 1 minus 2 is equal to n 2 C r 1 minus 1. So, we know that n C r plus n C r minus 1 is equal to n plus 1 C r or n plus 1 C r. So, n 2 minus 1 C r 1 minus 1 plus n 2 minus 1 C r 1 minus 2 by applying this formula is n 2 C r 1 minus 1. In a similar way, this is giving us n 2 C r 1. Therefore, the whole thing comes out to be n 1 minus 1 C r 1 minus 1. Again we applying the same formula, we get n 2 plus 1 C r 1. Therefore, if r 1 of small r 1 is equal to n 1 minus 1 C r 1 minus 1 multiplied by n 2 plus 1 C r 1 whole divided by n 1 plus n 2 C n 1. Thus, we get the marginal probability of r 1 taking the values small r 1 in the set 1, 2, 3 up to n 1. In a similar way, the marginal probability of r 2 can be computed for r 2 is equal to 1, 2 up to n 2, and it does not take much to understand that it is going to be if r 2 of r 2 is equal to n 1 plus 1 C r 2 multiplied by n 2 minus 1 C r 2 minus 1 divided by n 1 plus n 2 C n 1. Now, we accept the following theorem without proof. The probability of distribution of R, that is the total number of runs with n 1 objects of type A and n 2 objects of type B in a random sample is given by this complicated formula when R is even and this is when R is odd. Looks complicated, but we are familiar with this n 1 minus 1 C R by 2 minus 1 because it is even, say 2 D. Therefore, this is actually the D that we are talking about, and here also this is the D that we are talking about. In a similar way, when R is odd, it is 2 D plus 1. So, one has to be D, other has to be D plus 1, and by replacing 2 D plus 1 by R, we can get this formula. I want you to verify that because all the necessary mathematics we have already studied. Also, there is another interesting observation with respect to the runs is that if we define n 1 plus n 2 random variables r 1 1, r 1 2, r 1 n 1 and r 2 1, r 2 2, r 2 n 2, where r I j denotes the number of runs of type I, where I is equal to 1, 2 of length j, that is j is equal to, this should be j 1, 2, 3 up to n I. What does it mean? That means the number of possible values for R 1 is equal to 1, 2, 3 up to n 1. So, R 1 1 is number of runs of length 1, R 1 2 is equal to number of runs of length 2 up to R 1 n 1 is equal to number of runs of length n1. This is with respect to element of first type, that is A. Similarly, for B, what we get? R 2 1 is equal to number of runs of length 1 up to R 2 n 2 is equal to number of runs of length n 2. That is how we get R 1 1, R 1 2 up to R 1 n 1, R 2 1, R 2 2, R 2 n 2. So many variables, that is n 1 plus n 2 many variables, but let us note that if R 1 n 1, it cannot take any value more than 1, because if the length of the run is n 1, that means that all A observations are in that run. Therefore, there can be only at most one run of length n 1. Similarly, there can be at most one run of length n 2 with respect to the elements of type B. Now, note that sigma j r 1 j, j is equal to 1 to n 1 is equal to n 1, and j is equal to 1 to n 2 summation j r 2 j is equal to n 2. Why? Since r 1 j is the number of runs of length j, therefore, basically you are looking at number of runs of length j multiplied by the j, that is the length of that run. Therefore, when we sum over all the possible values, we get the total number of elements, which is n 1, and in this case which is n 2. Also note that sigma over j 1 to n 1 r 1 j is the total number of runs of the first element, and similarly this expression gives the total number of runs of the second element. Let me now describe a variation of the run test, which is called runs up and down method. This is applicable only for numerical data. Suppose we have a time series data and one may like to check if there is any trend in that data. For example, the number of cars passing through a corridor every day. It can be the number of infected cases of coronavirus on a daily basis. So, if we take the data for different time instance, which in this case are the days, suppose the data is increasing, then we can find a trend like this, which is an upward trend, or we may find a downward trend, which may look like this. And we are often interested in testing if there is any trend in the data or it is absolutely random. If we just want to test the randomness, we can split the data into two parts. Some of them are plus and some of them are minus, depending upon whether the sample value is above or below the median. This we have seen. For example, consider the table. If we have 6 time instance and the observed values are like this, therefore, the sample median is coming out to be 5.5, and therefore, what we are looking at, that these 3 are above the sample median and these 3 are below the sample median. However, in this type of test, we lose the information about the trend, because we have done similar thing with respect to sign test. Runs up and down test preserves the information about the trend. How it works? So, here what we do, given n time ordered sample x 1, x 2, x n, we construct an n minus 1 element sequence, which we call d n minus 1 of plus and minus, but its jth element is plus if x j plus 1 minus x j is greater than 0, and it is minus if x j plus 1 minus x j is less than 0. Therefore, from the same data, now we get a sequence of 5 symbols, but it is different from the one that we got for the sign test. Now, why this is plus? Because at time instance 1 the value is 8, at time instance 2 the value is 13, therefore, there is an increment, hence it is plus. From 2 to 3 the value has come down from 13 to 1, therefore, it is minus. From 3 to 4 value goes from 1 to 3, therefore, it is plus, here it is 3 to 4 plus, and here it is 4 to 7, therefore, another plus. Therefore, we get a different sequence here. Therefore, under the null hypothesis of randomness, the plus and minus are expected to be nicely intermingled, so that there will not be longer run of any of the two symbols, because if there is a longer run of plus 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 like that, what we understand that for the entire time period the value is increasing, that means there is an upward trend, and therefore, the value is not random. Therefore, here we look at the length of the runs, not the total number of runs that we have just seen with respect to Wald-Wolfowitz run test. If there is a long run of plus or minus, it implies that the data is showing some clear trend. Therefore, H naught will be rejected if there are r runs of some length t or more, where r and t are decided on the basis of alpha. That means, if there are large number of runs of certain length or more than that, then we are going to reject the randomness of the data. So, the method considers the number of runs of length j, j is equal to 1, 2, 3 up to n minus 1, because the length of a run can be 1, can be 2, or maximum it can be n minus 1, because if the entire data is showing an upward trend, there will be one run of length n minus 1 all plus. For illustration, let n be equal to 3, therefore, there can be runs of length 1 or 2. Now, the 3 numbers can be arranged among themselves in 6 possible ways, each one of them is equally likely. Therefore, since n is equal to 3, we are looking at D 2 and it will contain runs of plus or minus or maybe mixture of that one. So, let us illustrate. Suppose we have 3 elements A 1, A 2, A 3. A 1 is the value obtained at the first instance, A 2 is the value obtained at the second instance, and A 3 is the value obtained at the third instance. Now, if A 1 is less than A 2 less than A 3, then D 2 is going to be plus, because A 2 is greater than A 1, and another plus because A 3 is greater than A 2. Therefore, we get a run of length 2. Therefore, what we are saying, R 1 is equal to 0, R 2 is equal to 1. So, what is R 1? R 1 is equal to number of runs of length 1, R 2 is equal to number of runs of length 2, and therefore, we get 0, 1. If A 1 is less than A 3, less than A 2, therefore, from A 1 to A 2 we get a plus, from A 2 to A 3 we get a minus, therefore, we get 2 runs of length 1, therefore, R 1 is equal to 2 and R 2 is equal to 0. We know that there will be 6 possible permutations. For each one of them, we calculated the value of R 1, R 2, and we are getting that 2 instances of 0, 1 and 4 instances of 2, 0, as it is clear from here. Corresponding to each arrangement, we can compute the value of R 2 and R 1. Hence, R 2 and R 1 represent the number of runs of length 2 and 1 respectively, as I have indicated before, and therefore, F 3 0 1, this is the notation, which is actually the probability that we get a 0 1 sequence. That probability is 1 by 3, and F 3 of 2 0, that means we get 2 runs of length 1 and 0 runs of length 2, that probability is going to be 2 by 3, as we have seen just now. Now, let us generalize it. If there are n samples, we can think of f n, that is the probability of R 1, R 2, R n minus 1, where R 1 is the number of runs of length 1, R 2 is the number of runs of length 2, and R n minus 1 is the number of runs of length n minus 1. It is obvious that R n minus 1 cannot be more than 1, because if there is run of n minus 1 many elements, whether plus or minus, that means it has taken care of all the transitions, and therefore, there cannot be any other element in the sequence. Therefore, there can be only one run of length n minus 1. But if R n minus 1 is equal to 1, then all other values are 0. However, if R j is greater than 0 for any j n not equal to n minus 1, then R n minus 1 is equal to 0, because then we can never have a run of length n minus 1. If R 1 is equal to n minus 1, then all others are going to be 0, because we have got n minus 1 many runs of length 1, that means it has to be plus minus or something like minus plus like that. R 1 can never be equal to n minus 2, which is pretty obvious, and sigma over j R j, where j is the length of the run and R j is the number of runs of length j. So, that gives us the total number of symbols in the run, and that is going to be n minus 1. However, the basic question is how to compute these probabilities f n, R 1, R 2, R n minus 1. So, in order to compute these probabilities, we need to count the number of possible arrangements of n minus 1 signs of plus or minus, and which leads to definition of n minus 1 random variables, where R 1 is the random variable denoting the number of runs of length 1, similarly R 2 and up to R n minus 1, and we are looking at the probabilities of these variables taking the value small r 1, small r 2 up to small r n minus 1. So, let u n r 1, r 2, r n minus 1 be the number of possible arrangements, so that we can get the runs of these numbers. Therefore, f n r 1, r 2, r n minus 1 is going to be u n r 1, r 2, r n minus 1 divided by n factorial, because that is the number of ways of arranging n many elements. For illustration, with respect to the earlier example, u 301 was 2, u 320 was 4, therefore, f 301 was coming out to be 1 by 3, f 302 was coming out to be 2 by 3, as we have seen from this table some time back. Now, question is, how do we compute all these u n's? Basically, there is a recurrence relation which helps us to get u n from u n minus 1. So, suppose we have n minus 1 observations a 1, a 2 a n minus 1. An extra observation a n is added. Now, addition of this observation can either split an existing run or increase the length of a run, or it can introduce a new run of length 1. For illustration, consider 4 data points a 1, a 2, a 3, a 4 and such that it is in increasing order. Therefore, in D 3 we will have plus plus plus, because from here to here plus, here to here a plus, and from here to here there is another plus. Now, suppose the new element A 5 is such that it is the largest of all, then what will happen? We will get another plus here on the top of the 3 plus, and therefore, it is increasing the length of this run of plus. Instead, if the fifth element comes at the very first instance, then here we will get a minus, because A 1 is less than A 5, but after that there is going to be plus plus plus. Similarly, if A 5 comes at the second instance, then we will get plus minus plus plus, and similarly for all the 5 cases. Note that here we have assumed that A 5 is the largest element. Therefore, introduction of a new element will change the pattern of the runs of plus and minus. So, as we have written, in case of 2 and 5, the insertion introduced a new run of length 1. As you can see, here we get a minus, here we get a minus. But in case of 3 and 4, an existing run is split into 2 parts, because here it was plus plus plus, that is split into plus minus plus plus, and accordingly you can see that the values are changed. As we have indicated, now it is taking as 2 runs of length 1, 1 run of length 2, and no runs of length 3 and 4. So, the entire calculation is done here. Let me not elaborate that, let me go further. Now, if the initial arrangement of A 1, A 2, A 3 and A 4 is different, instead of that they are increasing, and then the effect of introducing A 5 will also be different, as the arrangements of the plus and minus will depend upon the relative order of A 1, A 2, A 3, A 4 and also A 5. Hence, we need to look for a generalization. In fact, we can identify for mutually exclusive and exhaustive cases as mentioned below. So, suppose S n minus 1 denote the number of arrangements with n minus 1 many elements of plus and minus, then an additional run of length 1 can be added in the arrangement of S n because of the introduction of the new element that we have already seen, or a run of length I minus 1 in S n minus 1 can be changed into a run of length I in S n. That means that an existing run is now increased by length 1, or it can be split into 2 parts. Here we have divided that also into 2 different segments. Suppose H is 2i, that means it is an even number and the new element comes at the middle. So, it may split it into run of length I followed by a run of length 1 followed by a run of length I. That means, suppose we had something like this and the new element converts it into plus plus minus plus plus. So, this is the case that is taken care of in point 3, but more generally, if the length is h, which is I plus j, I and j are different numbers, then it can split it into a run of length I followed by a run of length 1 followed by a run of length j. That means, the split is not equal. For example, we can have plus 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 divided into 3 parts, plus followed by a minus followed by 3 plus. So, here I is equal to 1, j is equal to 3. On the other hand, it can also split it like plus 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 plus, it goes to plus 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 minus plus. Therefore, I is equal to 3, j is equal to 1. The overall recurrence relation between un minus 1 and un can be obtained from the following formula. As you can understand, this is pretty complicated. We are not deriving it here, neither I am asking you to check the correctness of these things. It is only for you to conceptualize how runs up and down works. Now, Levin and Wolfowitz have computed the means and variance of number of runs of length t or more. For n less than equal to 14, the exact probabilities of getting at least r runs of length t or more are also available, and they are tabulated, and from there the critical regions can be constructed and H naught can be tested against suitable alternatives. However, when the number of values is large, we can go for normal approximation for the same, and the calculations is the following. The mean is coming out to be 2n minus 1 upon 3, and the variance is coming out to be 16n minus 29 upon 90. As you can understand that these are little bit complicated, so I am not going to derive the formulae, but if n is greater than 25 and if we incorporate the continuity correction, then we can get the left tail and right tail critical regions by using normal approximation as follows, that for the left tail it is r plus 0.5 minus the mean divided by the standard deviation has to be less than equal to minus z alpha, where z alpha is the critical value for normal distribution. Similarly, for right hand tail it is going to be r minus 0.5 minus 2n minus 1, which is the mean divided by the standard deviation. So, this is for one sided, and if you want to do it two sided, then replace z alpha by 2. Okay, friends, I stop here today. I think you have understood the intuition behind using runs for testing whether a given data is random or not. I stop here, and in the next class I shall study some more tests based on two samples. In particular, I will look at Kolmogorov-Smirnov two sample test and median test for testing the equality of distributions. Okay, friends, thank you.